All right, welcome everyone. Go ahead and grab a seat. Welcome to your first advanced physics seminar. Now, I know you've all spent your undergrad years meticulously mastering the foundational rules of the universe. But today in this explainer, we're going to do something a little bit different. We're going to completely dismantle our most basic assumption about reality. Yep, we are talking about the emergent illusion of causality.
Before we even glance at a single equation on the board today, I want to pose a Socratic question to you, one that directly challenges your intuitive everyday experience. Are you ready? Does a cause always precede an effect? Think about it. You push a book, it moves. You drop a glass, it shatters. In our human day-to-day experience, the answer is a resounding, obvious yes. But what if I told you that down in the bedrock math of fundamental physics, the universe literally does not care about cause and effect?
So here's our roadmap for today's session. We'll start by abandoning common sense, then look at the Galilean paradigm shift, the missing cause in physics, entropy in the arrow, why we're hardwired for narratives, and finally wrap up with an emergent reality. Let's get right into it. Section 1. Abandoning common sense and the price of scientific progress. To really grasp this illusion of causality, we first need to remember the last time human intuition was just fundamentally, massively wrong. You see, common sense is usually the biggest hurdle to a real scientific breakthrough. Just think back to the transition from a geocentric to a heliocentric universe. I mean, every physical sense tells us the Earth is totally motionless, right? You don't feel like you're hurtling through space at thousands of miles an hour. Geocentrism aligned perfectly with our gut intuition. But heliocentrism, that was based on mathematical models, telescopic observation, and abstract reasoning that entirely defied what people saw and felt every single day. And just look at this. This brilliantly illustrates the incredibly complex geometric reality early pioneers like Galileo and Copernicus uncovered. Look at all those intricate lines of sight. To actually accept the heliocentric model, humanity had to do something totally unprecedented. They had to trust the math over their own lying eyes. They had to accept that their localized earthly perspective was actively tricking them. Keep that in the back of your mind, because we're doing the exact same thing today with the concept of time and causality.
Okay, moving on to Section 2, the Galilean paradigm shift. Let's see how moving from Aristotelian natures to unified matter totally shattered the old world order.
So, before Galileo, Aristotelian physics ruled the day. Aristotle basically split the universe into two distinct realms, the corruptible, ever-changing Earth, and the perfect, eternal heavens made of, ether. But then Galileo points his telescope up, sees actual mountains on the moon and moons orbiting Jupiter, and completely obliterates that boundary. He asserted a unified corporeal matter, meaning the heavens and the Earth are made of the exact same stuff, governed by a single quantitative physics based on proportional math. He even formulated an early principle of inertia, basically realizing motion is conserved unless something messes with it. And boom, that was the birth of modern mechanics. Which brings us to Section 3, the missing cause in physics. Where exactly are the arrows? Because with classical mechanics born and formalized by Newton, you'd naturally expect cause and effect to be a cornerstone of the equations. So let's see if we can find it. Let's walk through this timeline together and pay close attention to how causality behaves. In 1687, Newton hands us F equals ma. We instinctively read that as force causes acceleration. But mathematically, it's just an equality. It goes both ways. Newton's third law says every action has an equal and opposite reaction. It's a symmetry of interactions that totally ignores any preferred direction in time. Then, jump to 1865, Maxwell gives us his equations for electromagnetic fields. They beautifully show how fields propagate, but they're local differential equations. They don't inherently dictate that a charge causes the field in a strict chronological step-by-step way. Then we hit the 1920s, quantum mechanics. We get Feynman's path integrals, Schrödinger's equation, complex amplitudes, the whole shebang. And throughout this entire centuries-long journey, as our physics gets more and more advanced, the strict one-way concept of causality just keeps fading further and further into the background. By the early 20th century, people finally started calling out this glaring omission. The philosopher Bertrand Russell famously realized back in 1912 that our fundamental physical laws express patterns. They express symmetries and correlations. But they do not express one-way arrows of influence. Our most fundamental equations are just remarkably silent on what causes what. So here is the absolutely crucial takeaway. The fundamental laws of classical physics, electromagnetism, and quantum mechanics all possess something called time reversal symmetry. They simply do not care about the difference between the past and the future. If you run the equations of fundamental physics perfectly backwards, they still make 100% mathematical sense. At the microscopic bedrock level of the universe, causality, it literally doesn't exist. Right, on to section 4, entropy and the arrow or the birth of the macroscopic world. This lands us squarely in front of a massive paradox. If causality isn't in the raw math, where on earth does the arrow of time actually come from?
Let's use a super simple analogy to break this down. Imagine a hot cup of coffee sitting on your desk. Step 1, the coffee is hot. Step 2, that heat irreversibly dissipates into the cooler room. Step 3, well, actually, there is no step 3 where you sit there and watch a lukewarm cup of coffee magically extract heat from the air to spontaneously boil itself, right? But here's the kicker. The microscopic equations totally allow that. It's just statistically virtually impossible. And that is governed by the second law of thermodynamics. While the microscopic laws are time-symmetric, macroscopic systems absolutely are not. Entropy, which you can think of as a measure of disorder, tends to increase. Because our universe started in a highly special, very low entropy state, we get this incredibly robust temporal orientation. Our everyday, common-sense experience of cause before effect is born entirely from out-of-equilibrium statistical mechanics. It's a macroscopic phenomenon, guys. It's not a fundamental law of nature. Moving to section 5, hardwired for narratives. Let's dig into the biology of cause and effect to answer the ultimate question. If causality is literally just a statistical illusion, why are we humans so stubbornly, obsessively attached to it? To really get this, we have to look at biology. We live in this big, messy, macroscopic, out-of-equilibrium world. Over millions of years of evolution, our brains were not shaped to sit around pondering time reversal symmetry or quantum amplitudes. Nope, our brains were shaped to survive. And to do that, we have to exploit reliable regularities in our environment. We are literally hardwired to detect patterns and compress massive, complex amounts of correlations into simple, actionable stories so we can predict what happens next. You see a sudden rustle in the grass, you assume a predator caused it, and you run. You don't wait to check the math. Russell pointed out a fantastic example of this. Think about night and day. Night obviously doesn't cause day, and day definitely doesn't cause night. They're just correlated effects of a much deeper mechanism, the Earth spinning on its axis. And yet, because event A follows event B so reliably, our brains desperately want to link them with a causal arrow. Confusing correlation with causation isn't just a mistake we make. It's practically baked into our human reasoning because it's such an incredibly efficient survival tool. All right, take your seat securely because we're bringing this masterclass to its grand paradoxical conclusion. Section 6, an emergent reality. How in the world do we reconcile the cold math with our everyday intuition? So what's the modern status of causality? Well, relativity doesn't give us a universal clock. Instead, it gives us light cones that strictly restrict the geometric bounds of who can influence who. Quantum theory? That gives us probabilities and correlations, not neat little causal chains. The inescapable truth we keep arriving at is that causality is not a primitive, base-level element of reality. It's an emergent, contextual concept. It emerges when you combine time-symmetric microscopic laws, a universe with a low entropy past, and our very coarse-grained, biologically limited human perspective. As the literature brilliantly sums it up, causality is more a working hypothesis than an experimental fact. It is absolutely indispensable for human existence. We literally cannot think, act, or make our morning coffee without it. And yet, our best, most fundamental equations of the universe are surprisingly reluctant to even acknowledge it. So I want to leave you with this final, somewhat provocative thought as you pack up your notes and head out of the lecture hall today. Just as humanity once had to let go of the absolute intuitive certainty that the Earth was standing perfectly still, you now have to let go of the certainty of cause and effect at the microscopic level. If the universe functions perfectly fine without it, what other common sense assumptions about reality are you still clinging to? Keep questioning, keep trusting the math, and I will see you all in the next session.